last class we were trying to find out the volt second average, that is the average variation of the pole voltage waveform used for our space vector PWM. That means for switching between in a sector the vectors forming the sector, that is 2 active vectors and 0 vectors. So, for sector 1, so we found the T0 is divided into 2 parts, that is T01 and T02, and placed at the start and end of a sampling period. And the next sampling period, the sequence is reversed. That means the first sampling period is T01, T1, T2, T02. Next sampling period is T02, T1, T2, T01. And T1 and T2 are the periods during which the active vectors forming the sector are switched. And T1 is for the vector which is at the start of the sector. That means if the rotation is from the anti-clockwise, it is start of the sector, and T2 is the end vector. So, for the general expression, we got for sector 1 Va0 average, Vb0 or Vc0 average. If you see here, these equations are irrespective of the sector. So, if you know the T1, T2 in a sector, we can find out the average value in that sector. So, let us see what is the average value in sector 1. This is easily we can get by substituting the value of values of T1, T2. T1, T2 we have already found out. So, let us go to the next page. Let us again write for our clarity Vs0 average is equal to, in sector 1, this is in sector 1, Vs0 is equal to Vdc by 2 divided by Ts, Ts is the sampling period, into T1 plus T2. Okay. Now, Vb0 average, that is average variation, that is why we are dividing by Ts. This will be equal to Vdc by 2 divided by Ts into minus T1 plus T2. Since the T0 periods are equally divided at the start and end, and for the start if it is 0 is used, end it is 1 1 1, and equal duration the volt second they will cancel. So, T0 will not come into picture for the average variation. Now, V0 average equal to Vdc by 2 divided by Ts into minus T1 minus T2. That means, this also equal to minus of Vs average in sector 1. Okay. Now, we have already found out the values of T1, T2 in our previous column. So, for our reference, let us note it here T1. T1 is equal to Ts into Vs, mode of our reference space vector, divided by Vdc. That is our radii of the hexagonal structure, Vdc into root 2 by root 3, that is sin 60 is there. So, that means sin 60 equal root 3 by 2. So, this will be 2 by root 3 into sin 60 minus alpha. So, alpha is measured from the start of a sector. So, alpha can vary from 0 to 60 degree. So, we are finding out the average variation in a sector. The sector is an equilateral triangle formed by the active vectors and the 0 vector. T2 is equal to again Ts into Vs mod divided by Vdc into 2 by root 3 into sin alpha. Okay. This is our. Now, let us put these values T1, T2 in equation 1 and 2. So, if Va0 and Vb0 average if we can find out, Vc0 average we can find out, it is only equal to minus Va0 average. So, let us say Vb0 average. This is equal to Vdc by 2 divided by Ts into T1 we will put Vs mod divided by Vdc 2 by root 3 into sine 60 minus alpha plus Ts into Vs mod divided by Vdc into 2 by root 3 into sine alpha. Okay. So, this we can, this is also from sin A plus sin B. We can use the standard trigonometric relations, and we can reduce this one to, finally it will come to Vs by root 3, Vs mod divided by root 3 into sine 60 plus alpha. Okay. Now, let us say what is Vb0 average. So, this is the one we require. So, in a sector with alpha vary from 0 to 60 degree, the average variation of Vs0 average varies like this, that is Vs by root 3 sin 60 plus alpha. Now, let us take Vb0 average. Now, let us see the Vb0 average. Is equal to, again, Vdc by 2 divided by Ts into Vs mod divided by Vdc into 2 by root 3 sin alpha minus Ts Vs divided by, we are substituting only the T1, T2 values into 2 by root 3 sin 60 minus alpha. So, this is the thing. So, if you see here, this will reduce to, Vb0 average will reduce to Vb0 average will be Vs sin alpha minus 30. Okay. This way it will happen. This is Vb0 average. So, now let us plot, let us find out, this only 60 degree. So, let us find other sectors how it works. So, let us go to the next page. We know our, let us draw our hexagonal voltage space vector structure. This will be like this. So, sector 1, they are all equilateral triangle. My figure is not that clear, but it is hexagon with equal radii. Okay, here. So, this is our sector 1, then sector 2, sector 3, sector 4, sector 5, sector 6, and switching sequence is 1 0 0, 1 1 0, 0 1 0, 0 1 1, 0 0 1, then 1 0. Now, so Vs0 average in sector 1, Vs0 average is equal to the sampled Vs, that is, this is our Vs is somewhere here. So, the sampled Vs magnitude into by root 3 sine 60 plus alpha, and Vb0 average is equal to Vs sine alpha minus 30 degree. Now, and Vc0 average is equal to minus Vs0 average. See, we want let us see the average variation for pole A. If you know the pole A average variation, pole B, pole C will be 120 degree phase shifted. So, in this phase, see our ABC phase will be, so far we followed the convention, ABC, this is A, this is B is in this direction, C is in this direction, C, A, B. That means A is along this axis in this direction. Now, A phase, so let us take the average variation along pole A, Vs0 average for a cycle. So, that means we are trying to plot Vs0 average for a cycle of operation. So, A phase is here. So, here we are also in space vector, average variation of the voltage space vector. So, when it is here, A phase will have maximum. So, let us take here, A phase will be minimum. So, omega t is equal to 0 is here. So, the voltage space vector rotates from here. When it comes here, A phase will have maximum. Here it will, when it comes here, it will be again 0. Here it will come, it will be negative and opposite. So, omega t is 0 starts from here. So, omega t, first let us see omega t 0 is equal to 0 to 30. That means, in sector 5, what is the average voltage, pole voltage variation for phase A from here to here? For that means, omega t is equal to 0 to omega t is equal to 30 degree. Okay. How to find out? If you see here, the average pole voltage variation is that switching is from 0 to 1, 0 to 1, and we know for the inner sector, if alpha is taken from the start of the sector, for here the start of the sector is here, for sector 1 it is here, the T1, T2 are the same in any sector, only the switching vectors are different. Now, let us find out the average variation, Vs0 average variation. It is varying. The switching vector is 0 to 1 here. So, but we have derived the equations for sector 1. So, sector 1 it is 0 to 1 is B phase. So, in sector 5, for omega t less than is equal to 0 to less than equal to 30 degree. See, now we are talking about omega t, general variable. The Vs, okay, or we will say the Vs0 average, Vs0 average is the same as the Vb0 average in sector 1, Vb0 average in sector 1. So, what is the Vb0 average? The Vb0 average is equal to Vs sin alpha minus 30 degree. Now, alpha we have to replace with omega t. Alpha to be replaced with our general variable omega t, with omega t. So, what is the relation between omega t and alpha? So, in sector 5, if you take when alpha is equal to 30, see alpha we are measuring from the start of the sector. So, from here to here it is 30 degree. When alpha is equal to 30, omega t is equal to 0. So, okay. So, what is the relation between alpha and omega t? So, this indicates that alpha is equal to omega t plus 30 degree. So, when omega t is equal to 0, alpha is equal to 30. Then omega t is equal to minus 30, alpha is equal to 0. So, that means in this equation Vb0 average in sector 5 from omega t is equal to 0 to 30, Vb0 average for omega t less than equal to greater than equal to 0, less than equal to 30 degree. That means from here to here, end of the sector, middle of the sector 5 to end of the sector 5. That means middle of S5 to end of S5, sector 5. What is the equation? We have to simply replace alpha with alpha in terms of omega t, that is equal to Vs is equal to sine of omega t plus 30 minus 30 degree. So, that is equal to Vs sine omega t. This shows this is only valid for omega t less than equal to 30 degree, less than equal to 0 degree. Okay. Now, the next what we have to find out, what is the Vs0 average from omega t is equal to 30 to 90 degree. So, now if you know that relation 0 to 90 degree we have found out. So, if the sinusoidal variation, if the average variation is sinusoidal variation, then automatically we can draw the other waveform from the symmetry. So, let us find out what is the average variation from for Vs0 from omega t is equal to 30 to 90. Okay. Again, let us go to the next page. This is our hexagon. With radii equal to VDC. Okay. This is the radii. This is 1 0 0, 1 1 0, 0 1 0, 0 1 1, 0 0 1, 1 0 1. Now, we have found out Vs0 variation from omega t, that is omega t is equal to 0 to omega t is equal to 30 degree. We know it, Vs0 average. Now, we have to find out omega t less than equal to 90 degree, greater than or equal to 30 degree. That means this interval. So, this is, if this is sector 1, sector 2, sector 3, sector 4, sector 5 and sector 6. Okay. And omega t less than equal to 30, less than equal to 0 degree, the Vs0 average. Vs0 average we got it from the previous slide, it is equal to Vs amplitude of the sampled reference phase vector into sine omega t. So, this you do not confuse with the continuous sine omega t for full cycle. This equation is valid only for our omega t. That is what do you mean by omega t? Omega t is the speed with which our reference space vector rotates. Okay, 0 to 30. Now, now we have to find out for omega t 30 to 90 degree. That is in S6. S6, if you see the variation of the switches is from 1 to 1. This is same as in sector 1 also. So, that means here the variation with respect to alpha, the alpha measured from the start of the sector, the Vs0 average is same as in sector 1. Only thing we have to change the origin. Vs0 average is same as the sector 1. That means Vs sine alpha minus 30 degree. Okay. So, if you see here, for alpha varies from in sector 6 is the same as alpha varies from sector 1. So, because the vector change is 1 to 1 here and here also 1 to 1. So, alpha varies from less than equal to 0 degree, less than equal to 60 degree, but omega t varies from less than equal to 90 degree, less than equal to 30 degree. This shows omega t minus 30 degree is equal to alpha now. That means when omega t is equal to 30, alpha is equal to 0 here. That is here. Omega t is equal to 0 means alpha is equal to 0. And omega t is equal to 90, alpha is equal to 60. Here omega t is equal to 90 degree, alpha is equal to 60 degree. So, here Vs by, okay, here one mistake is there, Vs by root 3 is also there. That I forgot, right. This is Vs by root 3 from the previous equation. So, now the Vs0 average is equal to Vs mod divided by root 3 into sine alpha is equal to omega t minus 30. So, this will be equal to sine omega t minus 60 degree. So, Vs0 average in sector 1 is Vs by root 3 sine 60 plus alpha, sine 60 plus alpha. Okay. Now, alpha is vary from 0 to 60 degree, that is from here to here, and omega t is vary from 30 to 90 degree. So, what is the relation between omega t and alpha? Omega t 60 plus alpha, that will be equal to omega t minus 30 is equal to alpha. That means when omega t is equal to 30, alpha is equal to 0. When omega t is equal to 90, alpha will be equal to 60 degree, that is from here to here. So, when you substitute this one omega t minus 30 here, alpha, the equation will be sin omega t plus 30 degree. So, Vs0 average for omega t varying 30 to 90 degree is equal to sin omega t plus 30. So, what will be the type of waveform this will generate? Let us try to plot the waveform. Write down the waveform. The required waveform for omega t is equal to omega t less than 30 degree greater than 0 degree. This is equal to Vs0 average is equal to Vs, the sampled Vs amplitude into sin omega t. Now, omega t less than equal to 90 degree greater than equal to 30 degree, Vs0 average. Equal to Vs by root 3 into sin omega t plus 30 degree. So, these are the two equations. 30 degree. So, let us plot this waveform. So, let us draw the angle. This is our y axis, okay, and this is our x axis. So, alpha is equal to 0 to 30 degree. That means here this is Vs, sampled value of Vs plus sin omega t. That means part of a sin omega t with amplitude is equal to sampled value of Vs and from 0 to 30 degree. So, this will be of this form, this one. So, this is our 30 degree. After this, from here to (90°). This is part of Vs by root 3. Now, the amplitude is reduced. Vs by root 3 sin omega t plus 30, and omega t varies from 30 to 90°. If you plot it, it will be of something like this. If you fix a Vs, then Vs by root 3 is this amplitude. Okay. Now, if 90°, so this again repeats. So, if you see, if you repeat this one for symmetry, it will go like this, 0, so the variation of our, see, we expected a sinusoidal variation and we got something like this. This is for the A phase. B and C will be 120° phase shifted, like this will be there. If you draw it, you can get it. Let us say the B phase will be like this, 120° phase shifted. Vb0 average variation. Okay. Then Vc0 average will be like this. We were expecting a sinusoidal variation and we got a waveform like this. So, what all this contains? Let us see. So, if you plot the line to line voltage, let us take the line to line voltage for, if you use, see, we know VA, VB, VC. If you can plot the line to line voltage, typical line to line voltage will be something like this, it will happen. See, line to line voltage is sinusoidal. Line to line voltage is the subtraction of two pole voltages. So, something common to this both the waveform, that waveforms, it gets subtracted and we got the line to line voltage. Now, what is that one? Let us sum all the three phases. If you sum all the three phases, what will get? If it has contained a triplen harmonics, you will get a waveform like this. So, that means the average variation contains a triplen order. So, triplen order, even if it is there, it will not produce an average voltage variation. Average voltage variation only due to the fundamental. The fundamental component of this waveform will be like this. Let us, the typical fundamental component, if you see, that we can get from the line to line voltage. The typical fundamental component for the A phase will be this one. So, that is sinusoidal. So, how to find out? See, we got the Va0, Vb0 pole voltages, Va0 average variation, Va0, Vb0, Vc0. Okay. Now, Va0, Vb0, you add Va0, Vb0. If it is contained only positive and negative sequence, then Va0, Vb0, Vc0 will be 0. But here it is not 0. We got a triplet order here. All the multiplication of the triplet, third, ninth, all that harmonics are there. So, you sum it and divide by 3. That is, you get this waveform. That is this waveform. This waveform, let us call V3. This you subtract from Va0 average. That means Va0 average minus V3. The triplet order you remove it. Then that will be our the sinusoidal waveform, this one. So, what is the advantage with the sinusoidal waveform? Let us say, even though triplet is there, the fundamental only will generate power. So, the moment you add the triplet, the peak of this one will be slightly suppressed. See, this is the level, this level, that is this level. The sine was there, it would have gone here. So, that means, and for sine triangle Pwm, if you use the same way with a triangle, we get extra modulation range. That means some more we can increase. So, in the space vector compared to sine triangle, we get a boost in the voltage. So, how much that boost in the voltage? Let us find out. Okay, this is our V alpha, this is our V beta. And maximum voltage space vector, we can get the maximum inscribed circle. This amplitude, let us say this OA is equal to our DC link voltage VDC. Okay. So, what is the radius of the maximum inscribed circle? This one, that circle will touch the hexagonal periphery here. So, this will be equal to 30 degree. This will be equal to, that means OC. OC is equal to VDC into cos 30 degree. That means cos 30 equal to root 3 by 2. VDC into root 3 by 2. So, as the voltage space vector rotates, that is our Vs rotates. When the Vs is along V alpha, as it rotates, we will have the V alpha, the magnitude of the alpha component will be maximum. So, V alpha maximum is equal to VDC into root 3 by 2. So, V alpha component we got. Now, we can find out what is the VA maximum. That will give the maximum possible from our space vector Pwm. So, let us go back to our alpha beta transformation. So, previously we found that V alpha is equal to VA plus VB cos 120 degree plus VC cos 240 degree. Okay. So, what is cos 120? This is equal to VA cos 120 is minus 1 by 2, VA minus 1 by 2 VB, cos 240 also minus 1 by 2, that is minus VC to 1 by 2. This is equal to VA minus 1 by 2 into Vb plus Vc. Okay. Now, we are talking about the sinusoidal components. For sinusoidal components, Va plus Vb plus Vc equal to 0. So, this will be Vb plus Vc equal to minus Va. So, minus of minus, this will become plus. So, this will be equal to 3 by 2 Va. Okay. So, V alpha maximum. What is V alpha maximum? V alpha maximum is equal to Vdc into root 3 by 2. So, what is Va maximum? Vdc into root 3 by 2 into, from this equation, V alpha is equal to, so V, if your V alpha is known, Va is equal to 2 by 3 V alpha. So, we multiply it by 2 by 3 here. So, Va maximum is equal to Vdc by root 3. This is the maximum. Vdc by root, that is Va maximum using space vector Pwm is equal to Vdc by root 3 is equal to 0.577 Vdc. So, you get in space vector Pwm, if you read our sine triangle Pwm, we got an extra boost in this one. How this extra boost has come? For sine triangle Pwm, when we use sine triangle Pwm, you have a sine wave and you have the triangle wave. Okay. And if you take the basic inverter configuration, one pole, A0, Va0 maximum, the sinusoidal average variation maximum is equal to 0.5 Vdc, sine triangle. Now, space vector, instead of the triangle, what is the waveform we are getting? Fundamentally, it's a triangle waveform, but actual variation is a sine plus a triplen content. That means something like this. Okay. This is the one. This is sine plus a triplen content. That is multiple of 3, triplen content. Then the Va0 maximum is equal to 0.577 Vdc. That means instead of using this sine wave, if we use this sine plus triplen, what we have some extra modulation. If you see here sine triangle Pwm, so extra range is possible here because this is flattened here. So, that is why we are getting maximum modulation of 0.577 Vdc. So, let us see what is the let us study what is the similarity between sine triangle and the space vector Pwm. Let us go back to our sine triangle Pwm. I will extend this one for your clarity. This is A phase. This is our B phase. Let us say this is our C phase. Okay. Now, let us say sine triangle Pwm. Let us the triangle Pwm is something like this, it goes. See, we are using a high frequency triangle waveform just for the analysis we expanded the waveform like this. Now, our triangle waveform is going from here to here, it goes like this. Okay. This is our A, B, C. Till it reaches this point, all the faces are, let us mark this point is some P. Till it reaches P point, triangle reaching the point P. Here all the ABC faces are above the magnitude of, till that one all the sine greater than the triangle. So, what happens? All the top switches are on. All the top switches are on, we are marking as 1, 1, 1. Okay. Now, from P to Q, P to Q, let us, okay, for my analysis, P to Q, here both are equal. P to Q, what happens? Till that one, A and B are above a triangle, but C is below. So, up to here, this the sequence, the inverter sequence will be up to here, up to PQ, the inverter switching states. Is 1, 1, 0. Here triangle up to the pitch, here it will be 1, 1, 1. Now, above that one, see here both are equal. So, above that one, then Q to S, triangle is greater than the sine wave. So, all the switches will be, it will be 0, 0, 0. So, Q to S, if you see here Q to S, these are 0 period, this is 0 period, this is also 0 period. So, if you see in sine triangle, the 0 periods which are, see vector, if you say here this vector switching, let us take another switching sequence, let us take another sequence here. Let the triangle is going like this. So, this I will mark, let some triangle, mark it as, let us say P, Q, then R, then S. So, PQ region, the inverter states. Is all 1, 1, 1, because sine is greater than the triangle. Then Q to R, B is below triangle. So, this will be 1, 0, 1. Then R to S, then let us see this is T. R to S, C has also gone below the triangle. So, that means 1, 0, 0. Then from S to T, it is 0, 0, 0. So, if you see here, same like space vector PWM, it is going from 0 state to active vector, then the next active vector, then here. So, it is switching between 1, 0, 1 to 1, 0, 0. That means 1, 0, 1 to 1, 0, 0, it is switching in S6. But here, in sine, same like sine triangle, space vector PWM, but the 0 periods are not equally distributed in a sampling period. What is the sampling period? Now, the triangle which going from P to T, that is this period, half of the triangle is our sampling period. So, during the sampling period, during a sampling period Ts, in sine triangle period, the zero vector periods are not equal inside. The zero vector periods are not equal in sine triangle. In sine triangle Pw. But in space vector, they are 0. But otherwise, if you see, when it goes from 0 to active vectors, only one inverter leg is switched. So, all other factors are taken care. Only the 0 vector periods are not equally distributed. When the 0 vectors are equally distributed, the average variation in the space vector becomes something like this. So, that shows this get flattened here. So, we can extra boost it, oh sorry, when the for the triangle waveform, it will be something like this. So, here, so we can get extra boost is possible, but triangle only this much only possible. So, this extra boost is possible, that will make the modulation index slightly increase in modulation in sine triangle Pw. So, we have talked about the space vector PWM. In space vector PWM, we require the instantaneous amplitude of Vs and the alpha, that is in the sector in which it stays, in which it is at the sampling period it stays, and the alpha angle is required to find out the switching intervals, that is T1, T2, T0. Once you do the switching interval various sectors, we will get a average variation sinusoidal with triple N addition. So, we get an extra boost in the fundamental voltage, because triple N's VA, VA plus VB plus VC is not equal to 0. So, that will not contribute to the space vector generation. So, we get an extra boost in the modulation index, and for the space vector PWM we will get 0.577 VDC. For the same with the sine triangle, it is 0.5 VDC. Now, next class we will study how to generate the PWM here, based only on there are various schemes available in literature. Here we will propose a scheme based only on sampled reference phase amplitudes, not based on Vs. We know that Vs is generated from VA, VB, VC. So, instead of sampling Vs, we will sample at that instant the VA, VB, VC amplitude, and from that one VA, VB will be rotating sinusoidally. So, from the VA, VB, VC, we will find out the timings T1, T2, a simple and fast algorithm for in digital implementation will be studied in the next class. Okay, thank you.